DVR 360 video. I don't know what that is. I do not know what that is. DVR. I don't know what DVR is. How to stop, how to start, and close captions, unlist live play. Unlist live replay. What does unlist live replay mean? Live replay. Just checking out something, and then we'll get started. We'll get started just now. What? What? That doesn't sound right. That doesn't sound right. I found a YouTube feature. I don't know what that means. Yeah, I don't want to unlist the thing. I just want my comments to stay on, and I don't think they do stay on. Okay, cool. Hi everyone. Welcome to Zach's. Welcome to Zach's stream today. And let's see, what are we gonna be working on today? There's a library called Libmpix. Libmpix. I like it very much. Libmpix. I try and contribute to it as much as I can. But Libmpix is an open source Apache 2.0 library to work with image data on microcontrollers, and it basically does image signal processing. It's an image signal processor. And this means collecting raw pixels or raw pixel data from your camera, and manipulating and mangling them as needed, so that at the end of the day, on the other side of your image signal processor, you get an image that you can use. So I'll actually just go. I think it's Bayer filter Wikipedia. This is actually what I want to look at. So this is how cameras work. Let's actually look at how cameras work. So cameras have an arrangement of filters in front of the sensor, and which we'll look at just now actually when we look at the documentation for RGBIR. But the camera filter, the normal the ubiquitous, or the most known camera filter, has a half green filter and a quarter blue and a quarter red. And then basically what the filters do is they are only excited by certain wavelengths of light. And red is a wavelength of light, green is a wavelength of light, and blue is a wavelength of light. And basically what a Bayer filter does is it enables us to sample a scene, process the data from the sampling, and then on the other end show what we sampled. So basically it works something like this. Number one will be the scene itself. What are you trying to take a picture of? Number two will be debayering. So basically number two is the output of data comes to us as how would I call it? Data comes to us as I don't know how to explain it. It's raw ADC values, and the ADC values indicate whether how much of a voltage was sensed by that part of the lens. And basically this is what we get, a black and white image. And then on stage 3, we kind of combine all of that data. We do something called debayering. And by debayering, we combine all of the red, blue, and green data, and in some other formats, we combine all of that. Some other formats have like yellow and magenta and all of the CMYK and all of those. So we combine that, and then we do something like denoising and or some reconstruction of the image, and then in the end we get this sampled image. This is what we get. This is what the digital camera shows you. And basically, in that couple of minutes, I've just run you through what an image signal processor is. It basically takes raw data from an image sensor. It does some manipulation on the raw data, and then on the other side, you end up with an actual image. So, what are we gonna do today? There's this library again. Going back, there's this library called Libmpix. And it's getting really popular. People are using it for a lot of their microcontroller cameras. So if you have a microcontroller system such as this one, actually that's the wrong one. Let's actually use the NXP one. So I was gonna show you this one, the camera and the microcontroller on the Nucleo. But this is Nucleo N6, and this one has a hardware ISP on it. So there's no need of actually doing ISP stuff on this one, because really it has a hardware ISP. You can't do software stuff, because if you need like more stuff, more features, you can. And I don't know that this one has an ISP. So this is a Freedom board. This is a Freedom board, and with a camera on top of it. What I want to demonstrate is, once you have that image data, the sampling data from your sensor, you need to do some manipulation on that data so that it actually becomes images that a human can look at and recognize as an image of something. Cool. So that's what actually Libmpix does. It's a processing pipeline that takes your pixel data and tries to produce actual colors that you can recognize. So what are we going to do today? Recently there was a request by one of the users of Libmpix that we work on, or rather, this has been coming for a long time. There's more than one request in the pipeline. But what we want to do is work on something called RGBIR. So RGB infrared, basically. And the sensor that is being used in this case is an OmniVision one, but this should be a very general thing that should apply everywhere. So in the end, we might use this to learn what it is and how it works, and then we'll make a generalized approach that we're going to build up. And I think what we're going to try and do today is mostly discover what needs to be done. There's a lot of data that I can use, but what we want to do today is mostly discover what needs to be done and then see where that goes, and then start working on it. And that's why this is part one, and there's going to be however many parts that it takes so that we finish this thing. Okay, cool. So actually, let's go. So let's read through this so we understand how this thing works, and then we can start breaking down what we need, because we need to get to a point where we understand what we need to do. And then once we understand what we need to do, we need to go and understand how we can't do it. Okay. So let's look at RGBIR technology as explained by OmniVision. So the RGBIR technology enables normal image capture from the same device, for biometric authentication, gesture detection, and all of that. Okay, cool. So that doesn't tell us anything. Number one, day and night vision in one sensor. So we're kind of learning what this is. OmniVision's RGBIR technology's ability to capture both RGB and IR images in one device allows for both day and night vision capabilities, making it the ideal choice for today's battery-operated security cameras and smart home systems. So this is quite cool, because immediately we can see where it's good to always know where the thing is applied that you're working on. And once you start knowing that it's used for this and that, and you start realizing you can see it everywhere in life. So basically what they're saying here is they have an image sensor that can work for both normal color pictures, so basically during the day, and also for infrared pictures, for pictures taken during the night. So let's actually just keep going and see what we can understand here. So number two, it enables biometric authentication. Today's mobile devices, PCs, and notebooks are LifeArbs requiring high level of access of security. And the advanced infrared sensitivity of OmniVision's RGBIR technology allows facial and gesture recognition. This is actually cool. Have you ever wondered why or how your iPhone is able to do facial recognition in the dark? This is why. Because this thing can still take the same image of your face in the dark, and using the feature analysis or feature extraction from the shape and everything of your face, basically this camera can sense your face. And because infrared light is, it's quite what is it, the wavelength is very long, which means it travels, what I'm saying, it's pervasive. There might not be light, but there's infrared rays everywhere. As long as your eye can see, I wouldn't even say your eye can see, like it just, there's the radio waves are there, and they can sample stuff, and you can always collect data using those waves. So let's look further. So technology featured. Color filter process. The OmniVision RGBIR technology incorporates advanced proprietary color filter process that improves color fidelity. That doesn't tell us anything. Pattern flexibility. Depending on the application's requirements, the RGBIR technology's extended flexibility accommodates 2x2 or 4x4 array patterning, consisting of 25% of its array to Flexibility accommodates for 2x2 or 4x4 array patterning, consists of 25% of its array to infrared and 75% of the array to RGB, to capture RGB and IR images in one sensor. Okay, cool. We provide dedicated RGBIR image processor and a companion ISP chip that extracts RGB and IR information separately. So there you go. So we can already see this. There's a sensor that is capable of taking both colored images and infrared images, and in this case the sensor is combined into one sensor, and you can use both of them at the same time. However, this last point is the thing that sort of moves it forward for us. We provide a dedicated RGBIR image processor and a companion ISP chip that extracts RGB and IR information separately. So it looks like you can, from one sampling, you can either take the RGB and you can either take the IR, or you can take this one and that one, and then you can keep both of them. But basically, during one pass, you can take one or the other, and you can do two passes if you want. Okay, cool. So application, mobile devices, security, computing, there's a lot of this. This is fine. We don't need to know this. OmniVision places its customers at the leading edge of imaging technology with a commitment to innovate, forward thinking, and solutions. That's fine. This is okay, cool. So we get to the part of the page that we actually want. So let's actually go through these definitions a bit, and then we can go. First of all, are there any questions so far? Let me look at the YouTube. So far, any questions? Okay, no questions so far. So let's keep going. What is RGBIR? Traditional CMOS image sensors employ Bayer format as a color filter array. This format allows each pixel of the CMOS sensor to be excited by a specific wavelength of light, which is what we said, which includes color and infrared. So cool. And while RGBIR enables infrared only light, while RGBIR technology enables infrared only light to be passed to the IR pixel. Okay, cool. So it's the same technology. So they have this filter format like we looked at here, and as we spoke about. So let's do a zoom in. So this pixel is only excited by red. This one also, this one also, this one also, this one also, this one also. Those pixels here, the active pixels here, are only excited by red. So they only let red through. And then the active pixels here, the green ones, are only excited by green, the wavelength of green. And they only let green through. And these ones are blue. So basically what OmniVision has done is in this arrangement, they've added another they've added another pixel into the grouping so that there's an infrared pixel that only allows infrared wavelengths to go through. That's what they've done. Let's keep looking at their documentation. So while RGBIR technology enables infrared only light to be passed to the IR pixel, and in the RGBIR color, relax. While RGBIR technology enables infrared light only light to be passed to the infrared pixel, in the RGB infrared color filter array format, because we just looked at a CFA, the CFA is a color filter array, I think so. Yeah, color filter array. In that CFA, several pixels have been converted to IR pixels, and the IR pixels are sensitive only to infrared light. Okay, cool. So let's look at this. By the way, did you know there's a way of naming this? You go this way, this way, this way. So you go 1, 2, 3, and that becomes BGGR. And then, so in here, this would be BGGI. Okay, and this one would be RGGI. And this one will be RGGI, and this one will be BGGI. So that's sort of like, there's never one that starts with green, because unless you start here and then GIBG, or you could start here and GBIG, something like that. Anyways, that's how you name a group of pixels. You go across one, diagonally down one, and then across one again, and that gives you the name of the pixel grouping. And that's where things like, let me show you. That's where things like, let's search for format here. Format. That's where, yeah, let's do formats here. Supported formats. Obviously, I'm zooming in quite less, and I should be zooming a bit more. It doesn't allow me to zoom in. Okay, cool. I'm zoomed in. So let's keep going. So there's supported pixel formats. Come on, show me. 8-bit formats. Yeah, RGB 332, RGB 565, RGB 24. These are all like pixel formats. But I wanted to look at the MPix formats. Huh? No, I don't want to look. I don't want to click on that. I don't want to click on that. I don't want to click on that. So, format. Yeah, format definitions maybe. There should be somewhere here. Yeah. So this is BGGR, GBR8, RG, GRBG. So this is how, if you want to understand how these pixels are named, it's basically from that shape that was on there. Okay, cool. So let's keep going with this. Let us keep going with this. Cool. It's been half an hour. So let's actually look at benefits and applications. OmniVision's RGBIR technology's ability to capture both RGB and IR images in one device allows for both daytime and night vision. So let's look at here. This is actually quite cool. So if you look at it, this is what they're saying. You can take the sensor, you can take a picture of a scene, and then this is the filter array that they have, and because of that you can either do a day vision or you can do a night vision. And the night vision will give you that, and a day vision will give you that. So that's basically what happens if you wanted to know. And that's cool. That's okay. We don't need to know more about benefits and application. We want to go towards implementation now. What is needed to obtain both visible and IR images with RGBIR image sensor optics side? So this is let's look at what the lens needs to have. So let's look at this. I love how documented these things are, because if they're this documented, you basically can always learn how to do this by yourself. Yeah, this is cool. Cool. So they have a dual band pass filter. I think we've done signal processing before, and we know about like band pass and types of filters. So they have a dual band pass filter, which means there's two bands that are let through. Anything else is not let through, and I think it's a section of infrared and the other, the visible light. So basically, let's look at it. So it says infrared to that much is let through. Look at here. So between it looks like between 1,000 and all the way to 800, this is let through. And then here, something like between just a little bit less than 400, it drops off at 400, and then all the way to just the middle of 600, before 700. So those two bands are let through, and you can actually see it here. And this is basically the definition of a night vision camera, or a dual vision camera, because it does visible light and infrared light. So this is the visible light band, it's let through, and then in here as well there's a sharp drop off and on both sides, but in here as well we let through infrared light, and it looks like we let through something like just over 800 to something like over 900 basically. We don't need to know the exact values, because by the time it gets to us, we can just use it. So this is fine. And this is quite important for the people who are building these kinds of things, camera lenses, and they want to actually make them. But I'm not building a camera lens, I'm using it. We don't make image sensors yet. We're just using them right now. So let's look at the next thing. What is needed to obtain both visible and infrared images with RGBIR image sensor ISP side? That's what we want to know. That's what we know, because that's what we want to know, because Libmpix is an ISP, and that's what we want to implement. So basically we want to end up adding RGBIR to Libmpix. There we go. Cool. So let's look at this explanation. What is needed to obtain both visible and infrared images with RGBIR image sensor ISP side? A companion ISP is needed to extract the RGB and IR information separately. So a companion image signal processor is needed to extract RGB and infrared. So the image signal processor could be a hardware signal processor, like the one contained on the Nucleo N6, or it could be a software signal processor, like the one in Libmpix, basically. Extract infrared image by interpolating sensors RGB and IR signals from pixels next to it. Okay, we'll learn this. Extract RGB image using the following formulas. R equals R minus X. X is pre-calibrated IR removal coefficient. So I'm having a difficulty understanding this. So it says R minus XIR, G minus XIR, B minus XIR. So they'll give us some sort of coefficient, and then we have to multiply that with the value that we get from the IR pixel. But let's look at how they are arranged. So if I want this green, I would do that green minus this IR. If I want this blue, I would do this blue minus this IR. If I want this red, I would do this red minus this. But then there's another one here. There's this one. So we have to kind of find out how to group them. Then they did say 2x2 or 4x4. So 2x2. So this one and this one, or 4x4. So 4x4. And that would be this one is connected to this one. This one's connected to this one, this one. So that would be 2. But okay. Anyways, we have some explanation on this. We're gonna walk through it. This is actually the part. To understand this is going to be more difficult than doing it, because once we get to a point of doing it, it's going to be quite straightforward. But I want to understand how it's done so that I can do this in my sleep. So that's the whole point of my stream. So to that effect, Libmpix has a how do I call it? A Discord community. It's a really nice one. It's quite open, and I'll do an invite to Libmpix. And what I want to edit this is no limit, never expire, generate new link, and I can copy that, and then I'm going to add that to the description of the video. So if you want to see that, it's going to be in the description of the video. It's going to be in the description of the video. Libmpix Community. Okay, that's perfect. Any questions so far? Any questions so far? Before we start understanding the interpolation. And as a cheat, I'm cheating here, but what I've done here is I went to the Libmpix community and I spoke to a few people, and they helped with trying to figure out how to do this. So we're going to go through the conversations we've had with the people in Libmpix, and then we're going to go through that. Any questions so far? I think what we're doing today is just discovery first, just to discover what needs to happen, and then we can go forward from there. Any questions so far? No questions. Cool. Let's actually look at this. So there's this in general you're going to find a thread for RGBIR in Libmpix. I urge you to follow that and look at it. So this is what Joshua says. Joshua is the person who wrote Libmpix, although now it has a lot of contributors. So I would say Joshua is the owner of Libmpix. It helps to think about the problem. It helps to think about the problem to have that outside. So let's look at this this sort of pixel array, let's say. So and then we have BGGI. That's kind of how we're naming it, BGGI. And we have an RGGI, and we have a BGGI and RGGI, BGGI, RGGI. So let's look at the other line. RGGI, BGGI, RGGI, BGGI. And it looks like that's the repeating pattern. So it's a BGGI and then an RGGI and then a BGGI. But if you go 3 by 3, it's different. Anyways, let's keep going. So, and think, for every position of the image, how do I gather a red, green, blue, and infrared value to push as an output pixel? Depending on the position, it is going to be very different for every pixel. So this is the part where we actually see how we manipulate the pixels themselves so that we come out with something. So depending on the position, it's going to be different for every pixel. For instance, if centered on an eye value, which is an infrared pixel, the eye value to pick will be that one. So okay, let's actually go here, and let's for arbitrarily pick something. So if I am here and I want to determine the red, the green, the blue, and the I, RGBI, if I want to determine all of those, this is what I need to do. So the I value will be that one. Okay, let's look at the G value will be an average of those up, down, left, right. Let's look at it. So if I'm here, up, down, left, right. That's it. I understand. I really understand. Oh my word, this is what we needed. Let's open Excalibur. This is now, it's really easy if we actually if we have the images we want. If we draw everything now, Excalibur. Amazing. So let's actually just build this up slowly and see what happens. So Excalibur, let's go into Excalibur, and what was this? DCMI MPP. So let's actually do that. Let's take a pencil. Let's draw. Yo, I can never draw. Let's draw this. Let's draw some shape here. Okay, cool. And then I want lines, and I want to draw. This is straight down, and then this is straight down. Whoa. Something like here. And then this is another. Oh no, don't do that. Give me another pencil. I want to draw that. Just want a line, and I want to make the line go down like that. Okay, cool. And then this, it needs to be 4 lines, and I want that, and I want to put that there. And just to try and be uniform, I want to click on this thing, and then I want to make this pattern like that. And then I do want this line. I want a line here, and I want it to go like that. And I want the line. It's a 4x4, so no. Stay there. No, line. So let's go through again, and then in here I want to pick another line, and then I want to go that way. So we have a 4x4. We have a 4x4. We do have a 4x4. So let's come back here. Yeah, 1, 2, 3, 4. 1, 2, 3, 4. That's fine. That's what we have. And let's say this is B. And then let's come here. This is G. This is G. Let's come here. Let's take this one and put a G, and then let's put this one. Let's put this one. This one's an I. Okay, cool. And then obviously we can we? Okay, let's just actually draw it. Let's draw it. Doesn't matter, so that we can have the reference that we need. BGGI, RGGI. Okay, cool. RGGI. So, and then here, this is an R, this is a G, this is a G, this is an I, and then this is probably gonna be a red. Well, let's look. This is a red. Okay, cool. I know exactly what to do here now. So, A. This is a red. This is a G. No. G. Yeah. Cool. So, and then this is they're always half green. So G. This and this is going to be an I. And then this one is going to be a B again. I think so, if I'm not wrong. This is going to be a B. And then it's going to be a G, a G, and then it's going to be here. This is going to be a G as well, and this is going to be an I. An I. Okay, cool. So now actually let's look at this. I'm sorry that it's so zoomed out. Let me just zoom in again, like super massively zoom in, and then can I move? And it's Control A, and then what do I want? I would like to group all of these things so that I can actually move them together. Group selection, cool. And if I move it here, fine, perfect. Okay, so cool. Let's go to Joshua's hints, and then we'll reason it out together. So if you're, let's say, so all of these, let's now actually understand this. Each of these individual boxes is a pixel. Okay, each of these individual boxes is a pixel, and what we actually want to do is for each individual box we want to generate an R, a G, a B, and an I for that individual pixel, so that we have this value, these 4 values of colors that we can combine to make one color. Remember, all colors are generated from R, G, and B. So if we want to do infrared, we have to collect all the infrareds for all of them. If we want to collect RGB, we will have to collect RGBIR for all of them. So that, and anyways, whenever we are going to actually process this, we're going to need to do this in the format that is described here. Remember, this is the format that is described here, which is if we're extracting IR image, we want to interpolate RGB and IR pixels from it. That gives us the IR image. And if we want an RGB pixel image, we want to do for each pixel we want the R, the G, and the B, and then we want the IR, and then we want to do this coefficient manipulation with it. Okay, so that's cool. So this gives us a way to collect both images. So let's actually just walk through the Joshua has some pseudocode for us here. Let's walk through it and try and understand what is happening. And I think from the feeling I have already, I think I can already start to understand it. But it's good to kind of walk through this and understand it, and then we can come in tomorrow and just write code like it's magic. That's basically my intention. Or some other day, whatever day we want to do this. So for instance, if we're centered on an I value, so let's assume we're centered on an I value here. We're centered on this I value. So let's take this. No, let's not take that. So I want to take a pencil again, and then I'll make it red. And then let's say we're centered around this guy. Okay. I wish it was less thick. Let's do that. Let's do Control Z. And then we want to take that pencil. And then what we want to do, why is there an insect on my face? Okay, cool. So let's actually just draw a little thing over there. So let's assume we're centered around this. The I value will be that I, okay? The G value for this pixel, the G value for this pixel will be the average of this. So this will add G, add G, and then you can divide them by 4, and that will be the G value for this, the green value for that. And then let's see, the red value will be the average of the diagonal. So we are here. This and this will contribute to the red of this. The blue value will be the average of this, and this will give us that I value. That's it. But that's if we're centered on an I value. Let's actually consider something else. Let's pick the pencil, and then let's go into like a blue. Okay, and then we'll say, if centered on a green value, let's actually take green, and if centered on a green value, only one line of context around is needed. So 3 by 3 is enough. What is saying here is that if you have like this 3 and this 3, you can compute for this. You can compute for that. Okay. If one is centered on a green value, depending on which G it is, there will be a red value left and right, up and down, red, blue, and there will be an IR value left, right, up, down. So, okay, cool. We know how to make these colors. So if you're centered on a G value, so yeah. Where does the 5 by 5 appear? Okay, let me just think about this slowly. Only one line of context is needed, 3 by 3. Okay, cool. If centered on a green value, depending on which green it is, there will be, let's look at it. So if you're centered on this green, there's going to be a B and an R, and then there's going to be this B and this R. So G will be itself. B will be what? There will be a red, blue value left, right, or up, down. So let's go here. Red, blue. Okay. I. Okay, cool. And let's go here. Red, blue. I. Okay, cool. So we need to pick something else. Let's actually look at this big one. So G, I, red, blue. Okay, cool. That's not the one we want. So let's go pick another one. G, I, red, blue. Okay. Okay, cool. So let's say we are centered on this G. Okay. The G value will be the G we get, that value. The R value the R value here will be that R value. How do we balance this R value? That's a question. The blue value will be this blue value, and the I value will be an average of this one and this one. This one and this one. So we average this and this and get an I for this. We get an R here. It's that R, it's that R. B here is that one. Cool, fine. And then let's look at, there will be an IR value, left, right, or up, down to pick. If centered on red or blue value, the diagonals are always IR. So let's center on this blue. The diagonals are always. So if we're on this B is itself. So if we're on this B, blue is itself, and then G is going to be this G and this G. Okay, cool. And then I is going to be just I and this I. And then R, maybe it doesn't have I, R. Ooh, there's this I and this I as well. So it's going to be this I, this I, this I, this I average for that. And then G is going to be this G, this G, this G average with that. But then where's the red one? Maybe red is 0. Okay, cool. Vertical and horizontal are always green to be average. Self is red or blue. Opposite blue is far away. Opposite blue, red is far away though. What is the implication here? How do I sample blue stock red for this pixel? Okay, so let's just go back. Let's go back. So there's that. That's fine. This is good. We're asking the right questions. For every operation except when it's positioned on the red blue, there needs to be one line of context around. Okay, so for green and I, you need 3 by 3. So basically, for green, you need that 3 and this 3. So you need this line and this line and that line and that line, and that's enough. So that's 3 by 3. That gives you enough. For except position when red or blue. But when positioned on a green, or a blue, we need 2 lines of context around, 5 by 5. Okay, let's look again. So if I'm positioned on this, I need that, and so 5 by 5. If I'm positioned on this, it needs to be 5. So it needs to be 1, 2, 3, 4, 5. So we need, 1, 2, so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So 5 by 5 or 5 by 3? You're walking in a field in line and shopping pixels. Okay, harvesting 4 colors whenever you walk. There's always enough red, green, blue, and infrared in just 3 lines. Boom, boom, boom. That's fine. Boom, boom, boom. Okay, cool. And we do not process data pixel by pixel, but line by line. So in Libmpix, we consume this data line by line. Okay, cool. So that's fine. So we can either have GBG, GIBG, or BGGI, or GIRG, or we can have RGGI. Those are the 4 possible line patterns, or 8 if starting 1 column more to the right. So let's see. There's always an option of starting here. So IGR, okay, GRIG, okay, IGGB, okay, and then IGGB. That's IGGB. I already said that one. GBIG. Okay, cool. That's fine. When you can name these things, it's okay. considering that we're working on the second row, so considering that we're working on the second row, these are the rows, columns, so considering we're working on the second row, okay, considering that we're working on the second row, middle horizontal line, and harvest red, green, and blue IR for every position. So okay, here B, it's going to be G, averaged. I is going to be this one and this one averaged, okay, for this. And then red, I don't know. Cool, that is fine. And for each situation, we should have an obvious position where to pick the closest one. So I don't know where the red is going to be. Do I pick that one? The closest red? That's a question. It turns out you only need to, that's fine. This is implementation. I don't need to look at this right now, so it's fine. So this is blue. Red is the one after the green. So, and then if it's, this is red, this is my blue. So these blues contribute to this red, and this red contribute to this red. Okay. The close ones. Okay, fair. So that looks good. So basically what we want to do, yeah, that's okay. So let's remove this. Let's remove this and leave it. So this is basically what we want to do. Every time we're on a pixel, we need to decide. So B, the greens is going to be this one, the I is going to be this one. So if I use 3 by 3, this B is going to be G, the G for it. B is going to be itself. I is going to be this one. I'm okay with that. R is going to be this one and this one. So I'm just talking to Joshua. Let's actually just talk in public so that people can actually see what's happening. I'm sorry about this. This is a discovery session. Come on, my mouse just died again during a stream. This is boring. I'm kind of half tempted to move to a wired mouse at this point. So we are sampling after all, so it's not about getting the exact stuff. We're sampling, and anyways, the 10% logarithmic thing about our perception is not going to, if there's, we can only see in groups of 10%. So basically, if you have a color level of 127, you wouldn't know the difference between 127 like 115 or something like 114. So 10% is like, yeah. sorry, I'm the 5%, 5.3 little, but if I can pick the this is fine. So we can probably pick the nearest neighbor. So let's now actually can I do Control Z Z Z Z Z Z Z Z Z Z Z Z Z Z Z, and I would like to extend this thing. So let's actually do 1 2 3 4, and I want it to be. I'd like to extend this to. Let's actually draw a different one. Control Z. Let's take this one and let's draw a different one here, and then let's actually draw 5x3. That's cool. We're almost done. So this one is going to be this is a discovery stream, so don't worry about it. We will do this practically, I think, tomorrow or something, but on live, on stream, so that way we never lose people. And then let's go here, let's draw that, and then let's take that, and we can do the second one, and then we can go right, we can do the third one, yeah, and then we can move this one a little bit. No, I don't want you to bend. Oh, crap. And then I'm gonna do that, and I'm gonna draw the fifth one over here. Yeah. And I'm yo. Okay. Just be straight, please. You as well. Just be straight. Cool. And I'm gonna click on that, and I want to actually reduce the length of this, reduce the length of that, reduce the length of that, and let's actually label this. Let's do A. So B, A, G, G, I, R, G, G, and then let's keep going. Here is R, G, no, G, G, I, B, I. And then let's actually go back here and see what we want to look at. I want to look at this. I want to look at this part. I want to look up here so I can see what I want. I want to see the full one. So there's BGRG. So this starts being B again. This starts being B. Okay, BGRG. BGRG, BGRG, BGR, G, R. So the thing I want us to do is actually have both of them. So let's actually let's shrink this as much as we can, because this was a bit much. So let's shrink this and leave this on the side here. We can leave this here, and then let's draw another 3x3 one, so that this time we have let's take a different color and draw a 3x3 one here, so that we have both variables, because if we have both of them, then we can look at it and it's quite easy to use. So that's fine. This goes across, and let's take another line here, and this goes across, and then let's take a different line here, and this goes down, and let's take a different line here, and this goes down. So this is fine. So we'll see which ones need more context. So this is B, and then this is G, and then this is R, and then G, then I, then G. Okay, cool. Come on, just let me click here. I. Put you on the side. Can I please just get a, oh my word, what is happening? Can I please get something here? Can I just get a letter? Yeah. Let's delete that. Okay. This is I. This is G. This is R. This is G. This is B. Okay, let's actually look at this again. So which one needs 3 by 3? Which one doesn't need 3 by 3? So it helps to think about the problem. So which one needs to think? Only one line of context is needed. This is if we're centered on an I value. Cool. So if we're centered on an I, we need this. That's it. Because on an I is the I itself, and then G is the average of G, and then B is the average of B, and then red is the average of. So to get here, to get the G here, to get the red, to get the G here, you go G. Okay, wait. I need a pencil. So G, and G, and then RGB. So you have an here, okay. And then to get the red, you go like red, and that gives you the red here. And then to get the blue, you get the to get blue, you go blue, and then you get the blue here. And then to get the I is I itself. So to get the I, let's put I as this. You put the I to get the I. No, foreground. So some odd colors. So let's actually just cover that with that. And then to get the I, we'll get an I here. That's how we get it. So that's fine for the I. However, it looks like only one line of context. If centered on a green value, depending on which green, there will be a red, blue, right, blue on the side, and there will be an IR value left, right to pick. But which one needs? But when positioned on a green or blue, we need 2 lines of context. So green or blue, we need 2 lines of context. But when positioned on red or blue, so let's look at it. This is I. So if centered on a G, the blue and the R of this one, if centered on a G, the blue and the R of this one, seems to me that the blue and the R is this one. So the blue and the R, then I have a G and the I is this one. So I have a, so it feels like I can go blue is blue, and then that gives me a RGB here, and then green is that green, so that green is here, and this is the green, and this is the RGB, the green there, and then the red is going to be that one. So this is going to be the red, is going to be here, and then the RGB is here, and then the I is going to come from here, and I'm going to label that this is the I, and then it's going to come from here, RGBIR. So so I want to draw arrows. So this is an arrow going, no, Control Z. So I'll draw an arrow here. This goes up there, and then the blue here, I want to take the blue here, and then I'll say this blue goes, I'll take an arrow here, and then now Control Z, and then I'll click aside, yes. And then that one, I want to draw an arrow here, and then this one, I want to click red, and then I want to draw an arrow here. This I want to delete that, this I want to delete that, and I'm going to take an A and I'm going to make it green, and I'm going to say here G, like that, and then print screen, and I want to only take this one. I think this is okay. Okay, cool. So it's been a really awesome session today. This is exactly what I needed to do. I just needed to sit down and draw these things and discover these things, because basically what is happening here, once we can arrange the pixels in our, we can arrange on the table, we can just use sketches and arrange a pixel the way we know, the way we need. It's easy to write the code that does this. That's basically it. And basically, I think for today, I'm gonna go back to the Libmpix community. All of you are welcome. You can join us. You can join Libmpix. There's a link in the description. Come join us and come work it out with us. Let's see what happens. But what I'm gonna do is probably we will figure out all the pseudocode and all the algorithms here. Then I think by the next time we work this out, we're going to actually be able to just write the code for it. But this is it. Thank you so much for showing up today. That was me. I'm Zach, and what we're working on today is adding RGBIR to Libmpix, which is an ISP, well, image signal processor. Thank you so much for showing up today. Cheers, everyone.